This is a talk that's kind of come out of my being at Brown for 3 years and listening to the planetary guys talk about the moon. This is my first foray into the moon. And it comes about from thinking about how we're going to produce this mg spinel anorthosite that M cubed has seen on the lunar far side and on the lunar near side, on the Moscoviense crater and the Theophilus crater. So this is a collaboration between a whole bunch of people, Liang and Mac Rutherford over in the petrology group, and Carly Peters over in the planetary group, and a whole bunch of grad students and postdocs who, as usual, have done most of the work. And just the crystals here, these are actually terrestrial pink spinels, or what are often called ruby spinels. They're almost pure MgAl. And these are when we're talking about this pink spinels on the moon, these are the kind of crystals we're looking at. How do I get it to, oh, there we go. And what I'm going to try to convince you of is that to make these Mg-rich spinel lithologies, particularly the high abundance of spinel that the M-cube data suggests, that we're going to need more than just normal crystal fractionation processes, and we're probably going to need a reaction between an orthositic crust and some low iron melt to produce them. Okay, so what are the features of these pink anorthosite regions that I think are kind of interesting or kind of unusual that we need to explain? Here is image from Carly's paper that was shown earlier. The pink regions are where they've detected spinel being a dominant phase. I think the red is the pyroxene-dominated areas, and the green is the olivine that we were looking at earlier today with the diviner data. This is from Moscoviense. So one of the interesting features is the high abundance of spinel, particularly in the Theophilus crater. Deepak, who's a grad student who's been working on this, is saying that something like 30 volume % of the rock should be this Mg-rich spinel, which is quite high. Spinel, iron and chromium-rich spinel, is a very common phase on the moon, but it tends to be kind of in the 1 to 5%. How do we get 30 volume % is going to be an important part of this tale. Equally interesting is the absence of mafic minerals in the regions where spinel has been detected. So yes, there are olivine and pyroxene-rich regions near the spinel regions, but in the spinel regions itself, there's no detected olivine or pyroxene. It might be there in a very small abundance. And so we'll need to explain that with whatever model we come up with. And then the composition of the spinels themselves look very pure spinel composition. That is very low iron, very low chromium content. We're still working to figure out exactly how low in iron, and we're synthesizing spinels to measure in relab for their near infrared. It might be, once we've got these produced, we could look at them in the far infrared. Basically making spinels with a range of iron contents in the lab. And so we have to figure out how to make these unusually low iron contents. And then, at least in the Moscoviense area, what are these, do these olivine and pyroxene-rich areas have some relationship to the spinel-rich regions? An important point to make here is that pink spinel, or this pure spinel, has been seen, or similar minerals have been seen on the moon before. This is an image of a pink spinel troctolite. So this is an olivine plagioclase-rich rock. This is from Prince, 1974. Haggerty saw similar spinels. The difference here between this rock and what Carly is seeing with M cubed is, one, the presence of olivine, which is fairly abundant in these rocks. In this image, the spinel, which I've circled in the pink circle here, looks quite abundant, but in fact in the rock it's less than like 6 or 5%, which is lower than what Carly's seeing. And then the composition, this is an analysis of these spinels. We see this is 7%. This is on the low end for these rocks. Normally it's more kind of 9 or 10%, and that's a little bit high for what Carly is suggesting. So here's a kind of a typical fractionation model in a diopside forsterite anorthite ternary. If we imagine we have kind of basaltic lunar melts down here, they would typically fractionate, olivine, orthopyroxene, eventually get down to anorthite. Potentially we could make troctolites. Paul Warren has written papers about interacting these melts with the anorthositic crust, and potentially you can make troctolites. What is hard to do is to get up into this region where we'd have just anorthite in spinel. So it's hard to explain. In the kind of fractionation model, you'd end up with high fractionation fractions of olivine, pretty limited amounts of spinel. Even if you did end up with a composition over here that would fractionate to the olivine spinel binary, this is a reaction point. So to get beyond it, you actually have to consume the spinel. So then you have to start talking about crystal settling, which might be an alternative hypothesis to make these spinel-rich layers. The problem is the spinel that you would fractionate from these fractionated melts would be iron and chromium rich. And so it's not clear that you could match the right composition. As I said, Paul Warren had a nice paper talking about how AFC processes, assimilation, fractionation, and crystallization processes, kind of magma chamber processes between a basaltic melt and ferroanorthosite. You can get melts to go from kind of the normal crystallization sequence to pyroxene down to plagioclase. You can get over to this join between olivine and plag and make troctolites. So this is his model for making troctolites. And you can see the issue we need to do to get to spinel. We're going to need to interact it with a lot more ferroanorthosite to pull the compositions over here. There are examples on the Earth of interactions between very olivine-rich lithologies, very feldspathic lithologies. This is from the rum-layered intrusion off the coast of Ireland. This is a bit the flip side of what I'm going to talk about for the Moon. We've got a feldspathic melt coming in contact with an olivine-rich solid, and this black material in between is spinel. So just to show you that whenever you're going to react a feldspathic-rich material with an MgO-rich, olivine-rich material, it'll pull you onto that anorthite spinel join. All right, so here's kind of the concept. We have basaltic melts down here, and we have our ferroanorthosite up here. If we have small amounts of anorthite or anorthosite crust mixing into the basaltic melts, we can imagine it assimilating. Basalt assimilating anorthosite will be down here, and maybe we're making the troctolites and the spinel troctolites. But if we have the flip side, where let's say we have an anorthosite being invaded or metasomatized by a basaltic melt where your proportion of anorthosite is very high, you'll be up here, and you could potentially end up on this anorthite spinel join. So I'm an experimentalist, and there have been experiments done to look at these sorts of interactions, but mostly they've been aimed at looking at the composition of the melt. So these are experiments from Fanilla working with Mac Rutherford in 1994, and then more recently Zach Morgan working with Liang, Olive Brown actually. This is a plagioclase capsule and a green glass melt, and Liang used a slightly different geometry. This is his green glass, and then he put a solid layer of anorthosite on the top, and then watched how the green glass dissolved the anorthosite. But again, he was very interested in the liquid compositions. But you can see, and this picture is a zoom in of this square, that it produced spinel in the liquid just below the anorthosite. But they didn't analyze, unfortunately, they didn't analyze these compositions. And what I'm interested in looking at is actually the anorthosite layer. If we think of this as a model for the lunar crust, did we produce spinel in those? So what we've been doing over the last couple months is running very similar experiments, but with much larger pieces of anorthosite, and then looking inside of the anorthosite to see what's being produced by melt-rock reaction. So if we want to think about it, these experiments were kind of more modeling the troctolite, high melt, low anorthite mixing proportions. The experiments I'm going to show are more high anorthite, low spinel. High anorthite, low melt proportions. So here's the result, kind of quickly. This is looking in the anorthite region of those experiments. This kind of dark gray is the plage. We can see the melt is this light material surrounding the plage. And then here, all throughout this anorthosite, is some spinel. And we get 10, we've even kind of gotten close to 15% in these experiments. And then, so we've got the volume percent. We could talk about ways to get that higher. But what's interesting is to look at the compositions. So this is iron, magnesium, and chromium in the spinels. The experiments are the circles. Our normal experiments are these guys. You can see we make about 10% iron in our spinels, which matches the pink spinels in the troctolites, which are these triangles, quite well. What it doesn't do is match Carly's constraints, where she wants to have less than 5% iron in her spinel, so to the left of this green line. We do have an experiment that reproduced that. It was actually a failed experiment where the capsule popped. The FO2 reduced greatly, and we smelted out half the iron in the melt. So we produced a very low iron melt, which produced low iron spinels. So the suggestion is that you can produce these kind of spinels by this reaction with the green glass. If you want to get down here, you need a low iron melt, and maybe something like the parents to the MG suite. Not sure. And so this is my final slide, just showing the idea being for this talk. You have an orthositic crust. We have a range of melts from Mari compositions to maybe MG suites that come up through the anorthositic crust. They're going to have to react. And what we're seeing with these spinels is potentially the range of melt compositions. And what we're going to do looking forward with our experiments is to look at different compositions of melts, look at the spinel compositions in more detail to see if maybe we can tease out the depth at which these reactions are taking place, temperatures, and potentially kind of source regions. Thank you.
Any questions? Well, if not, that will keep us on time. And that's good.
I got it. With regard to your spinel experiments and the modal abundance, something that I've asked Carly many times is how much spinel do you need to get the spinel signature? Is it 1%, 10%, 50%? And have you looked at that with your experiments? Have you looked at the spectral reflectance of your experiments too?
Not yet. So one of the things we would like to do, and the nice things about these experiments, I guess it's gone now, is we could actually cut out that little piece of anorthosite, and maybe over like 10 experiments, we could generate enough that they could do the spectral reflectance sign. We can also just generate spinel and anorthite individually in the lab with the kind of right composition, and then mechanically mix them as well. And look at that. I think it's a real open question. I think Carly would be very, I don't know if Carly is, oh, there she is. Carly keeps telling me, we're still working on the phase proportions, and how much exactly it is not clear. But it's more than the couple of percent that is normally abundant. So it's definitely higher abundance, whether it's